Welcome for today's live session. So this is week 6 live session for advanced research trends in smart grid technologies, and I'm TA for live session for this course. So I'm Gagan Meena and I'm doing PhD at IIT Bombay in Electrical Engineering Department. So let us begin today's session. So this will be the agenda for today's session. We'll first of all go through a very brief overview of the week 6 material, topics covered in the week 6. Then we will discuss some questions. And while discussing questions, we'll also go through some important concepts. Then finally, we can have a doubt. If you have any doubt, you can ask. Even in between, also, you can ask your doubts regarding what has been covered till now in the course. Just to remind you that deadline for assignment 7 is 15th March and for assignment 8 is 22nd March. And the live recording of these sessions, recording of these live sessions is available on the link. It's also available on the portal. The link for the Google Drive of slides as well as the channel link is available on the problem solving section of the portal. Let us then begin with the overview of week 6. In week 6, we broadly discussed these 4 topics. First topic was the continuation of the same topic which was discussed in week 5. So in week 5, we were discussing the smart grid protection issue and techniques used for smart grid protection. So we discussed that the conventional overcurrent relay is not sufficient and we need to add the directional element to it. So we need both directional and overcurrent element in distribution system because of the bidirectional power flow. As a result of the integration of DERs. If we consider this simple feeder, and if we have a relay here, and a relay here, and we have a source here. If there is a fault here, F1, then this relay will only detect a fault in this direction. So, but if this is islanded, in the islanded mode, this source will not be there. And if there is a fault, the current will flow like this. But this result, if there is no directional element in the relay, then this fault will not be detected. So we need a directional relay. So we have another relay here, and both these have directional element. So these are both direction plus overcurrent relay. So now if we have a fault current like this, then this R2 can detect the fault. So current in this direction will be detected by R1. So this will be a forward fault for R1. So fault in front of R1. Similarly, if you have a current like this, then it will be a fault in front of R2. So both can detect. So we can detect the fault current in both the directions. Only if we have directional elements. So this we discuss in week 5. But we need to adapt. One thing was this direction, requirement of direction element because of the bidirectional current. Then Then we need the adaptive protection. So we will discuss why we need adaptive protection also. Then after that we discussed this modeling of energy storage. Some concepts of this were already discussed in week 3. Then modeling of DC microgrid components, like we saw, we will see again this one also. And then final topic was the operation of AC microgrids. So now we can discuss that why adaptive protection schemes are required, why the conventional schemes will not work. So we this was the motivation for the adaptive protection schemes. So because of first we discussed just now we discussed that because of the difference of so first reason for the need of adaptive protection was this bidirectional fault currents because of DERs. Then second is this different modes of operation of microgrid because we have this microgrid. We have two distributed generators here. So this is the circuit breaker. So there are two cases. One is when this is connected, so grid connected mode, and second is the islanding mode. So in both the cases, if there is a fault here, F2, so in this grid connected mode, fault currents will be there will be 3 fault currents. But if islanding mode is there, this will not be there. So there will be change in fault currents. But if we go with the traditional conventional methods where we have fixed setting of fixed relay settings, then we may have problems because these DGs also they have a limit on the fault current. For inverter based DG, as we have discussed, it's 2 per unit, and for synchronous based DGs we have around 5 per mode. So all these problems require us to adapt the relay setting based upon the operation of mode of the operation, as well as uh, the it also depends on the type of DG. So if there are inverter based and synchronous based, both type of DGs are available, then also the setting will change. And if for some reason one DG is out, maybe for maintenance, then we may have different configuration of DGs. In that case, also the relay settings will have to be changed. So so this is the second reason. Then this third also we discussed that there is a difference in level of fault current because of type of DG. So all these are the problems which require us to go for this adaptive protection. So where we can deal with both type of mode also, it should be able to distinguish. It should be able to differentiate between the different DGs also. So for that, we have discussed some techniques in the week 6. So these are the techniques. So both two techniques were discussed. Both were based upon the superimposed adaptive sequence current based. So one is they use sequence current, and another is they use the superimposed component. In the previous week, we discussed the techniques which were based upon both The conventional directional relay is based upon both voltage and current, right? We discussed that this voltage is taken as the polarizing quantity and current is taken as the operating quantity. This is the conventional directional relay. Then we check this phase angle, and based upon the phase angle, we determine whether the fault is in front of the relay or behind the relay. But here we are using only sequence current. We are not using voltage. We are only using current, and that too we are using the superimposed component. So let us first see the two techniques. So first one was this positive sequence component superimposed current base. So here we use only positive sequence component for identifying the direction of fault. But for backup current, we are using the negative sequence current. For primary, we are using positive sequence current. Here also for primary, positive sequence current is used. For backup, negative sequence current is used. But for directional estimation, in the second technique, both positive sequence and negative sequence superimposed current are used in the directional element. This is for increasing the reliability. So if suppose here we consider only positive sequence component. So if the positive sequence component is not able to detect the fault, maybe in case of some like impedance faults, then the negative sequence will be able to do that. So we are taking the both these two input from both the two. So this technique is more robust in that sense. Also here we are also considering the impact of type of DG. So this impact factor in the overcurrent relay settings, it will be able to factor in this 2 per unit and 5 per unit limitation of fault current in the inverter based and the synchronous based DG. So here the fault current will be multiplied by this impact factor. Impact factor. So because for inverter based DGs the current is less. It is only 2 per unit. So we want to increase it. So this impact factor in case of inverter based DGs will be more than 1, so that the fault current is increased. Similarly in synchronous based, so we may need to reduce the fault current, so impact factor is less than 1. So is it okay? Is there any doubt in this?
Uh,
Yes.
yeah, regarding this IF,
Hmm.
as
Yeah.
earlier I understand, IF will be more for synchronous type DG. In earlier lecture, it was like that.
No, IF we have in earlier lectures we have not discussed this IF.
But the clamping inverter is having some clamping effect. Fault current is more in synchronous type of DC. No? It will go to
Yes,
4 to 5 times.
that
Is
is
any
correct.
relation with that and IF? That is my question.
Fault current is more in synchronous based DG. That is correct.
Yeah,
So what we are the problem here is if suppose inverter based DG is also there and synchronous based DG is also there.
yeah,
So inverter based DG has limit of 2 per unit. Okay, the fault current
yes,
will be limited to 2 per unit, and
true,
for
yeah,
synchronous based it is 5 per unit.
yes,
So there is a difference. lot of difference between this. So what we are trying to do, we are trying to increase this and reduce this so that we can make them equal, almost equal. So let's say 3.5. So this impact factor, what if it is, because it is more than one for this inverter based, so it will be 2 times x. This x is greater than 1, so this will make it near to 3.5. It's just example. Similarly, for this synchronous based, this x factor will be less than 1.
Okay.
So actual current output from these two will be same, 2 per unit, 5 per unit. But the relay will see a current which is more from this inverter based. So impact factor will do that. We are trying to minimize this gap.
Okay. So how it is done? Which is done through any circuitry who
So
limits this? Yeah.
this
Okay,
is
then.
then this is coded inside the algorithm. So that
Okay.
algorithm will make multiply this current with the impact factor.
Okay. Okay. Now clear. Yeah.
Okay. So any other doubt?
No, you can proceed.
Okay. Okay. Let's move further
And
on. Yes.
yeah,
Yes.
one basic doubt regarding positive and negative sequence currents.
Hmm.
Whose elements are responsible for more negative sequence current part?
Whose
Type of the elements, like inductive load or capacitive load or resistive load.
if
Who will
resistive?
that will also
Hmm.
govern things in a network.
So when generally these are, since we are talking about the microgrid, so we are mostly concerned about the distribution system. And in distribution system, there is unbalance.
Yeah,
Unbalanced three phase loads are not balanced.
yeah,
So because of this unbalance, there are these positive negative sequence components. So positive sequence component in normal operation, it will be there. Positive will be there, negative and zero will not be there. But if
yeah.
unbalance is there, negative and zero may also be there.
The fault condition is also one type of unbalance. No? Fault
Correct,
is
correct.
also one type of unbalance condition.
That is true. So fault is also unbalanced. So in
Yeah,
transmission system also, although three are balanced, but under faulty condition, it becomes unbalanced. So the negative sequence component and zero sequence also come into picture. So here in distribution system, without fall in normal operation, we also in normal operation also we have these negative sequence component because of unbalance.
okay,
So
okay,
it is always there in distribution system.
okay, okay.
So
Right,
in
right.
fault condition, it will increase.
It will increase.
Yes.
Only you have to take care for that.
Yes, that is why this technique we are using,
Yeah,
because in normal condition also we are having sequence current.
yeah.
Otherwise, it may not work.
Mm.
So we have both negative sequence and positive sequence currents.
Right, right. Please proceed. Yeah, right.
Okay, so then we discuss this modeling of energy storage. So we discuss what is the importance of energy storage. So can anyone tell why do we need energy storage? How energy storage can help in microgrid setup? It's something we discussed in previous, I think week 3 also. So if you recall something, okay. So one is this, in microgrid we can see we have these day, solar and wind. So in solar, mostly we have excess generation during the daytime, and but our load may be generally we have this evening peak. Load has a evening peak. So what we can do, this excess solar we can during daytime we can store it in the battery, any kind of energy storage. Then in evening peak, we can discharge it to meet the requirement. Similarly, this wind also, generally the maximum power from wind is observed during late evenings or in night. So we can store it and then use it during daytime. So energy storage can help us in this. And this is possible because our excess generation from these sources, the period during which they generate excess is it does not coincide with the maximum the peak demand period. So we are able to exploit this fact. Then in islanded mode, storage can help in balancing energy balance, maintaining this balance between load and generation by properly charging and discharging. Then it can help in flattening the load curve. So if this is a load curve, so the ideal load curve is like this. This is the ideal one, where the installed capacity is very close to the actual requirement. But generally, we have one or two, even more than two peaks, maybe possible. So if this is a condition, then what happens? We need excess generation during only a small period of the entire day, and rest of the time, this generation will not be used. So it will be not efficient for these generators. So we always want this load curve to be flat. So somehow, if we are able to shift this area to this region or this region, then we can have a close to flat curve. So what can be done? This can be so we can fill this area by charging the storage. Similarly, this also during this time we can charge, and this area if we can discharge. So we can achieve this a flat load curve. So this because we are shifting this energy from one time period to the another. It is also called energy time shifting. Still, let me erase this. Then we discuss this type of storage, energy storage. This we also discussed before in week three. So we are mechanical, electrical, thermal, and electrochemical. So these are different type of mechanical: pumped hydro, compressed air, flywheel. We can also have gravity based. Then electrical fuel cell, semiconductor material based, and supercapacitor. Then we have thermal and electrochemical. Then we discuss different battery terminologies. Then type of batteries like lithium ion, nickel, metal hydride, nickel cadmium, lead acid. sodium sulfur is also there. We have different types of batteries. Then we discuss the modeling of battery and supercapacitor. And finally, some factors which affects the battery performance. Then after modeling this energy storage, we moved on to this modeling of DC microgrid components. So first we saw this importance of DC. So can you tell what is the importance of DC over AC? Why are we already have this huge network of AC system? Why do we want to move to this DC microgrid?
A control is easy. It's a
Okay.
very easy to control. That is the main key area in my view.
Okay. And
Control part.
what else? That is correct.
Losses also far less. Only we are using two-wire systems.
So
If you are going on HVDC side, then only two wires are used for transmission. So
so
losses will also be less.
so,
Easy control, and then losses part, control part.
so
Then
these yes, these are the advantages. Okay. And what
yeah,
else? But why? Uh, Even before also DC was providing uh, these advantages, but why the focus is now as why the focus is increased now?
well, because nowadays a lot of complication grid connectivities are taking place. So but control day by day is becoming complex.
But why
I
the
think
control is becoming complex? That you are missing.
lot of network additions are taking. Micro gates are
Hmm.
being added.
So
Lot of
why?
local
Yes.
generations are being added.
Hmm.
Earlier, one generating station, transmission line,
Hmm.
distribution step down. So complication was less. So control was also not uh, complex. You can say.
So one point you said correctly. So we have local generation. So what are this local generation? So what are the type of these local generations in microgrid?
Mainly solar,
Yes, correct.
wind.
So we are
These are
talking
mainly
about the solar. And solar, what is the output of solar?
basically these are DC.
Correct.
DC
So
output is
this
there. Yeah,
this is DC.
yeah.
And what are the loads? Majority like we have lightning.
Mostly in distribution system, mostly lighting is 50% almost. So
So,
lighting load is almost resistive load.
so
You
is
can
it
say
a
DC load, DC load
so this is
almost.
DC because nowadays we are using these LEDs and these are DC load.
LEDs, yeah,
We are using converter because to convert AC into DC, but they are as DC load.
yeah,
And
mostly,
correct. So we have generation DC. So we have solar, fuel cell. Then we have loads also. Several loads are DC. We have
yeah,
these data centers. We have these communication towers. So all these are DC loads. And
yeah, yeah,
then another important thing is we need we just now in previous slide we talked about the importance of storage. And storage is also a DC load or DC generation.
yeah, yeah. Mostly DC load,
Correct.
storage batteries, and
So
mostly,
since we are talking mostly about batteries, so battery is a DC load. So
yeah.
we can say generation is also DC, load is DC, and storage is also DC. So why not use a DC microgrid?
Why
So
not
that
use?
a DC
D-
microgrid.
Yeah,
So this is the motivation for this for moving to DC microgrid. Although we cannot completely remove the replace DC cannot completely replace the AC microgrid AC system, but we can have a combination of two. But what should be that optimal combination? That depends upon many factors that we will see in the upcoming lecture hybrid AC/DC microgrids. So where can we use them?
yes, yes,
Yes. So then
yeah,
we have DC at different voltage levels, Right now we have these HVDCs above 500 and above 800, 500 kV.
Yeah.
HVDC, we use them for asynchronous tie. So we are connecting our regional grids using these HVDC lines. Then we have this MVDC are at 11 and 33 kV. Then this low voltage DC that is for domestic purpose for residential grids. We can use it. Maybe 48 volts we can use for residential purposes. Then we discuss these different microgrid topologies, single bus, multi-bus, and reconfigurable topologies in that ring, zonal, empty DC. This is multi-terminal DC. This we will see further in hybrid AC-DC. Then PV, we discuss this modeling of PV, wind, and fuel cell. PV and wind we have already seen in week 2 modeling. It is same. The model is same. So we will not discuss it again. Then in fuel cell we discuss the equivalent circuit of fuel cell. Then also we also discuss this different types of load models. Constant current, constant power, and constant impedance. So can you tell that light bulbs, that incandescent bulbs that we used to have earlier, so they fall into which of these three categories? Constant current, constant power, or constant impedance? Any idea?
Should be constant power, because constant current, actually they are not pure resistance. They are having inductance part. They are not
In,
pure resistance. The element filament is not purely resistive load.
but it is mostly it is resistive only. So uh, it is.
But voltage, due to voltage fluctuations,
Huh. So if
uh,
voltage fluctuates, that is why if when there is a voltage fluctuation, we see that the intensity of the bulb changes because the
yeah,
power also changes because the
yeah,
R is impedance is fixed, resistance is fixed. Once we once the bulb is manufactured, it will not change. We are not using
yeah,
any variable resistance in that. So when the voltage dips, the intensity of the bulb also goes down. So
yeah.
there the impedance is constant, so voltage changes as the power changes as the voltage changes.
Power, the
Power
voltage,
output will change as the voltage is the input, so power output will change as the voltage varies. And voltage, is, since it is not always constant, there are some minor or major fluctuations. So based upon that, the power output will change.
voltage into current will draw more current. Power will remain same. Suppose
So
voltage
is it P?
dips.
This is P is V square by R. So R is constant. If voltage increases, power will increase. If voltage reduce, power will reduce.
Yeah, work like in a constant power mode only.
No,
Works
it
like,
is not. It is constant resistance. Na? R is constant here. So
yeah.
we can say P is proportional to V square. This is the
Yes, yes.
relation. So R
No,
is
no, no.
constant here.
Yeah, resistance is constant.
Hmm. That is
Voltage,
why it falls into this constant impedance category. And when we do this power flow analysis, it, uh, we generally consider one type of load. Which one is that? Can you tell?
we
When we do
normally consider resistance, impedance negligible.
no,
Consider,
I'm talking about this. Uh, when we do these load flow studies, so we model the load buses as PQ buses, right? We consider that they draw a fixed amount of power or active or reactive or both. So we model them as constant power. So this we do in transmission level, we do like this, but at distribution level we have so many types of loads, and the aggregation at transmission level we consider as constant power, but this does not hold good in distribution system. So we model these all these different types of loads. There is also one zip model, exponential. There are different other models are also there. So this zip is impedance, current, and power. So these three, a fraction of these three will be zip. 20% this, 40% this, 40% this. We can have like this. So we can have different types of model based upon, because different loads are not actually, they may not actually fall into DC category. Then we have to do some combination of the three. Let, shall we move? Right then.
Yes, yes. Please proceed.
Then finally we discuss the switch mode converters, where we discuss this. This can be isolated or non-isolated types, and we discuss these non-isolated types, which the conventional ones, buck boost, and buck boost converters. So this is the buck converter. So here buck means it will reduce the voltage. So if it is, let's say, 100 volts, and so here we can get nearly 25 volts. So all these work for around 1 to ratio of 4 times. So it can either increase, boost the voltage by 4 times, or buck the voltage by 4 times. So beyond the ratio of this 1 is to 4, we don't use these. Their efficiency is not good beyond this ratio. So beyond these, if we want reduction or means boost or buck operation, we go for the isolated topologies. So buck, so this is a boost. So this will boost the voltage, and here it can do both based upon this duty cycle. Can reduce also and increase the voltage both. So suppose this output voltage is 20 volts and input is 80 volts. So what will be the duty cycle? Can you tell? So this is the formula we're using this. Output is 20, input is 80. So D is output by input 20 by 80. How much? So here we are using the switching devices. So this will be on for this duration, then it will be off. This will repeat with the frequency. So this is done at high frequency. So the average that we get is, so suppose this is V out, and this is Vs. So for when the switch is on, so when this is on, this diode is not working because this is reverse bias. So when this is on, the entire Vs voltage is across this load. So we get this Vs, and this inductor is charged. When this is off, since this inductor is charged, this will discharge. When this switch is off, the inductor will discharge like this. So it will become, polarity will change, and this diode will start conducting. So this output will be shorted. Am I audible? We can say T on into Vs divided by Ts. So this is the average output voltage. And T1 by Ts we call it duty cycle. So this becomes, we call it, so if it is D. So V naught becomes D into Vs. Similarly for boost also we can do this type of analysis. So then we discuss operation and control of AC microgrid. Islanding we already discussed what are the issues with islanding. Then detection techniques we have seen is in previous week. Passive techniques are there, active techniques are there, and then hybrid techniques are there, and communication based techniques are there. And the main point of this thing is control of DGs. So we have synchronous DGs, inverter DGs. Synchronous generator DGs have their normal. We already have these generators, so they have the same control which is followed in the conventional generators. And inverter DGs can operate in islanded mode and grid connected mode, and they can have these three different types of operation. Then we discuss the ancillary services. These are the different types of ancillary services. So in normal operation, we can have frequency and voltage support, power quality improvement because reactive power support is there, congestion management, and in islanded mode. Sorry, this is not. It should be black start. So in islanded mode, it can provide the services. So let us move to questions now. So first question is this: what is the value of coordination time interval maintained between primary and backup relays? Can you tell? Suppose let us take only this conventional system. We have these two relays R1 and R2, and if R1 is the primary for this fault and R2 is its backup. So if R1 is not able to clear this fault, is not able to detect the fault, then this R2 will detect. So it will wait for some time. So what is that time? So if the time of operation of R1 is let's say 0.25 seconds, then time of operation of R2 will be time of operation of R1 plus this coordination time interval. And this we keep around 0.3 seconds. So the next question is, while estimating the fault direction using the superimposed currents, the sign of delta phi during the reverse fault when the power flowing in the upstream direction. So is it positive, negative, positive and negative, or none of the above? Can you tell?
Should be negative.
Negative.
Yes.
It's a reverse fault and power is flowing upstream.
Reverse fault
So
flows
let's,
upstream.
if we have a relay here, so it is a fault like here. Okay. So F1 is the reverse fault for this relay. Let us see this table. Ah, so this is the table. So this is the upstream, and we are talking about reverse. So what will be the, so now can you tell, will it be positive or negative?
So
If
upstream, then it is should be positive. Yes.
yes, correct. So here we can see this in downstream
Yes.
flow and upstream flow condition. So in downstream we have, so in this superimposed current based technique, what are we doing? This angle is between which two quantities? So we have the positive sequence fault current and positive sequence current before fault. We have these two values. We take their difference and this is called this superimposed positive sequence component. So this is the superimposed component. Now we have to take the angle between this superimposed current component and the pre-fault current. This this is the angle. If we see in this direction, this diagram, then this is the fault current and this is the pre-fault current. So if we, since this is fault current and this is pre-fault current, so this will be the superimposed component. Here we can see this I1 F1. So this is the superimposed component here. This we can see here this in the red phasor. And now we want the angle between this pre-fault positive sequence current and the positive sequence superimposed current. So this is the F1 for the fault. This is F1 behind the relay and this is F2. So behind the relay, so we can say reverse direction and this is the forward. So for reverse direction, this is positive because we consider this direction as the positive. So you can say this superimposed component is leading the pre-fault current. That is why the difference is positive. But if we see this second position F2, so here the superimposed component is this and the pre-fault current is this. The pre-fault current is leading. This is leading. And as a result, this angle becomes negative. Same thing you can see here. Is it okay? This question is done. The next question is this: in the two-bus system, the load is drawing to 50 ampere current from bus 1 to 2. Here we have a load which is drawing to 50 amperes, and after, when there is a fault at bus 1, the current, the fault current at the bus 1 is increased to 1600 ampere. This becomes 1600. So what will be the superimposed current at bus 1? So what will be the answer? Just now we saw this superimposed component is difference of fault current and the pre-fault current. Pre-fault current is given as 250. This is 1600. The difference is this is the answer. Now this is the next question. So you have to identify the backup relay for the fault F1. So if there is a fault here, so for fault F1, can you tell which one are the primary relay? This is for the grid connected mode. Jay, can you tell?
Backup relay,
No, so first tell me which is the primary relay for fault F1.
primary relay.
If there is a fault on this line, so which are the primary relays?
Primary relay for it should be R1.
So only R1, is R1 only sufficient?
No, no, no. Primary RV because there are two generators on this side also. So the backup relay will be R1 and R2 both.
No, primary.
Yeah.
First primary. We have to first see primary. So for a fault here, so for this line, we have this line has been protected by these two relays, correct? R1 and R2.
Yeah.
So if there is a fault, any fault on this line, these two will detect. So these are the primary relays. So
Yeah.
if we have a fault here and the fault current is like this, then R1 can detect if it is above its threshold.
Yes.
If we also have a fault current like this,
Mm-hmm.
and if it is above this threshold of R2, then R2 will detect. So both these relays are going to protect this line, this feeder.
Yes.
So,
Yes.
so first of all, now we are clear that for F1, the primary relays are R1 and R2.
Yes.
Now we have to find the backup
R3, I5, R5.
R3, R5. No. So we
Yes.
have to check that. So R3, R5. Are you sure?
Uh, R3, I.
Because see, this relay R1 is will see a fault. So R1 will see a fault in this direction. R2 will see check for this direction. R3
Yes.
will check for this direction. R4 for this. R5 for this direction and R5 R6 for this. Now again think and tell. So which one will be backup for R1 and which one will be for R2?
No, no. In that sequence, R4 and R6 will come.
Correct. So
Yeah,
for
R4
that
in
will
this
be
sequence.
for R2 or R1.
For R2.
Correct.
For R2, yes. For R2.
For R2, R4 and R6 will be there because
Yes.
they are seeing
Yeah.
this fault current.
Yes.
And we also have these two sources which are feeding. So they will be backup. For R1 there is no backup
R1,
because
there is no
here we
backup.
don't have any.
Yes. It's a very tricky question.
So it's a, so suppose if now can you tell what will be the so what are the primary relays for this F2 for F2 fault?
For F2.
Yes, primary relays for this F2.
For F2 will be R3 and R4. Both.
Correct. So both are there
Yes.
because we
Yes. Yes.
have current from this source here. So we from this
Yes.
direction we have current, from both direction we have current, and so
Yeah.
both will be protected. So for what will be the backup for R4? Is there any backup for R4?
No,
So
R4
R4
is
has
not
no
there.
backup. So what
Yes.
is the backup for R3?
R3, uh, R3 will have two backups.
Yes, which one? Uh, which are those two? What are those two? So
R6
correct. R6.
and also R2 will also act
No,
like as a backup.
no. Just check once again because we have to see this direction. Fault
No,
current.
no, R1, R1. Sorry, R1.
Correct,
R1,
correct.
this direction,
So
R1. Yes,
R1 and R6 both will act,
yes,
both can act
act
as backup.
backup. Yes,
So
yes, yes.
lastly, let us see this one. What will be about? What about F3?
Three
So for F3, primary relays are
primary relay will be relay will be
how?
R1, R4, and
R1 is only for this line. R1, R2. We are
R1.
talking. So we are talking about primary relays. So
Okay,
primary relay for this feeder, for F3 feeder.
okay. This feeder. Relay for voltage. Both will act, no? R6 and R5 both
Yes, so both are
primary.
primary
Yeah,
relay for this. So
F3. Yeah,
yes, so for F3, for R6, is there any backup?
R6. mm, R6 relay.
So we for backup we have to look here. We don't have any.
uh, Backup will R1.
No,
No.
no, for R6. This just like you said, na, for here for
Okay.
F2, is there any backup for R4?
Yeah, R4, R3 is the backup.
No, no. See the direction. So
No,
R4,
no. Okay, okay. Okay.
you have to see
R4.
this direction. You only just told that R4 has no backup. Just as R1 has no backup because behind this there is no relay. Because if suppose R1 fails, then
Yes,
the
there's
relay
no
which is
backup.
behind it should be
No,
able to.
no. Yeah, yeah. There is no backup.
So for R4 there is no backup. Similarly for R6,
R6 is also no backup.
no backup. So
No.
and what about R5?
R5,
Check the direction.
R5 is having backup from R1 will act as a backup. No.
R1 and Any other? Is there any other?
R1 this direction or R5.
Or R5? R1 is correct.
R1 is having backup and
Just check this direction. Is there any other relay which also feeds current in this direction? Means which can see current in this direction?
then R3 you can.
R3 is seeing a current like this. So current if goes like this or this. So for R3 the current should go like this, but R5 wants a current in this direction. So this R3 will cannot act as a backup.
Mhm. No relays there. Then R1 and R5 both
R5. What about this? So
five.
because this source is there, na? This source will feed a current like this,
Mhm.
and R4 is also protecting in this direction. So can
Yes,
then R4 can also detect, right?
yes. Now yes.
So
R1, R5 and yes, same direction.
yes, so we just have to check the direction.
Mhm.
So let us make it more complicated.
Yes, yes.
This was
Yes.
what we can do. This is grid connected mode. Now we let us consider the case where there is no grid, so it is islanded mode. Here is one source. We have one source here, and we have one source here. We don't have any source here.
Okay.
So this is R1. This is R2. Change that. So this is R1. This is R2. This is R3. R4. R5 and R6. So now let us see the same. We have fault F1 here, F2 here, and F3. So now tell me, for F1, for a fault F1, what are the primary relays? So
R1 will.
R1 will protect in this direction, R3 will this, R4 here, R5 in this direction, and R6 in this. Now you have to check. These two sources will feed current like this. Now if fault F1 is there, now you have to check which one will act as a primary relay for F1.
For what location?
F1 for this one.
R1, R2 both will be primary relay.
But here we don't have any source. If we don't have any source, how R1 will not see any current?
Mm-hmm.
Although yeah, you are correct in answering. It can act in grid connected mode. It was acting, but now it is of it will not see any current. Although it is meant for protecting this feeder only, but in islanded mode it will not see. So R1 will not be used here in this case.
Then
So
primary relay will be R2 only.
yes, so this in this
R2
case we have
only.
only one relay R2.
Yes,
R1
R2
will not
only.
see any current because R2 will see current from both these
Mm-hmm.
this DER1 and DER2 both one. So what now we have to see backup for this. So what will be the backup for R2? Check the direction just as we did in the
Yes, yes.
previous case.
R4,
So we
R4, R5, R4 and R6. These are
correct.
the two backup relays.
So we have
Direction action.
R4 and R6.
Yes.
Similarly, let us see about this F for F2. So for F2, which one will be the primary relay?
Uh,
See the all the possible current direction. For a fault
okay.
F2, what are the two current? How many currents will feed this fault? Then decide.
R3 R3 and R4 will be the primary relays
So
for
why are you
F2
saying R3 is also primary? Why?
because from it will see power from DR2 na, in same current direction.
Good. That is correct. So now we have to see backup.
Yeah,
So for
yeah.
R4, is there any backup relay for R4?
Any backup relay for R3,
R4. First, let us see R4.
R4. R4 is not having any backup relay.
No backup.
No backup.
Okay,
No backup.
correct. So for what about R3?
R3 is yes, R3 is having backup.
Which one?
R3 is having backup. From
So which relay will see current in the same direction as R3 is seeing? That we have to check.
R6 also see.
Correct. So if for F2 fault we have two currents. One is this,
Yes,
other
one
is
is this,
this. So now
other is this.
which? So which relay is seeing this current? R6 and R3. So R6 is the backup for R3, correct?
Yes. R3
Now is it clear?
yeah, yeah, it's clear, clear.
So for F3, tell me the primary relays.
F3 primary relays.
Yes,
F3, R5, R6 both are primary relays.
correct, because we
Yeah,
have current from here also and current
yeah.
from here also.
From this direction also.
So now tell me backup for R6.
R6, uh, R6 will have only one backup. R4.
R6, how R6 can have, because R6 you are saying R4 is saying current like this.
No,
This
no,
current
never.
will flow, so current
R6.
directions are not matching.
No, no, no. R6 is not having any backup.
Correct, no backup.
No backup. No
So
backup.
what about
Yeah.
R5?
R5. Yeah, R5 will see the backup.
Which one?
This will R4 will act as a backup.
Correct. So now you have understood it.
Yes, yes. Now, lot of time has. Now I'm
Yes,
through
it
it.
is an important
Yeah.
concept.
Yes, yes.
And
Now
also,
I'm through.
yes.
Yes.
Okay, good.
Yes.
Let
Now.
us move then ahead.
Yes. Yes.
So correct answer for this was R for R6. So now let us move to the next question. So fiber optic is an example of which of these communication network?
The wide area network. Wide
Correct.
area.
So it is wide area because we need it's over a long distance, high speed.
Yes. The backbone of present day communication.
Correct. We have undersea cables, fiber
Yes.
optic cables network is there. So entire internet is using that. Now, so next question is compressed air storage is a form of which of these? Electrical, mechanical, electrochemical.
The mechanical only.
Hmm. Yes, it is mechanical. Hmm. Next is which relay will operate under a high negative reactive power mismatch? Oh, oh, I think this question is wrong. Sorry for this is not the question. Question is uh, how do we measure the capacity of a battery?
Okay. The ampere hour, no?
Yes, correct. This is ampere hour. Or we can
Ampere hour.
also use watt hour.
Ampere hour or watt hour.
So generally, when we use this watt hour for
Yes.
we have all these this grid connected storage right now we
Yes.
can also find in gigawatt hour
Yes.
level. There is one 200 megawatt by 1600 megawatt hour storage. This is operational. So this is 1.6 gigawatt hour. So we have now storage capacity is increasing. So we have big projects. Recently, NTPC has also floated a tender for 9 gigawatt hours of storage.
Maybe in Rajasthan.
So
Maybe.
that means it is not it's for single location. It
Okay.
is for multiple location, and also they have floated it so that not that they have made it flexible that several entities can come up and fill this 9 gigawatt hour of storage capacity. Single, it, they need not to be a single entity.
Okay.
Several entities together can apply for this. This is the aggregate requirement.
Yes. Well, mostly generation is in western part, Gujarat, Rajasthan. They will.
It depends upon voltage level also. Means voltage in application. So in
Yes, yes.
future, the government has also come up with guidelines that after 2025, if there are new thermal plants, so they have to install because our target is to be net zero by 2070. So if new thermal plants are coming up after 25, then they have to ensure that around 40 to 50% of their installed capacity is they are procuring from renewables
Yes.
to ensure this net zero. So although thermal will be there, but still emissions we are reducing in net terms. So we are increasing both renewables and thermal. Thermal will not increase much, but if there are some plants, then they have to adhere to this guideline so that there is a boost to the renewables. Now, the next question is what are the benefits of the energy storage system? Improve the reliability, reduce system losses, reduce peak demand, provide endless service, or all of the above.
Totally, all of above.
Yes, so correct, all of the above.
Yes.
So their storage is reducing system losses because it is charging, it is consuming or even generating at local level. So it will reduce the usage of the network. So if we have generation and consumption at local level, then requirement of the network will be reduced. Utilization of network will reduce. So losses will go down. And just we saw that it can reduce the peak demand by doing this time energy time shifting.
Yes. Flattening of load curve.
Yes, correct. So all of the above. Now this is another question. Just see it carefully. So which one of these represent the equivalent model of a supercapacitor? So you have four options. This should be our
This first one.
correct.
A.
Correct.
A.
So this is the basic principle of supercapacitors. We know that Q is CV, right? and C is epsilon A by D. No?
Yes.
So if we want to increase the capacitance, what we can do? We cannot change this, but we
Yes.
can change this also. This is epsilon R. So this is epsilon naught into epsilon. Either we increase the dielectric strength, or we increase this area, or we reduce the D.
Yeah.
Reducing gap beyond a certain point is very difficult. How increasing distance is not a problem, but reducing distance is a problem. We cannot reduce D to a great extent. But so what supercapacitors are doing, they are increasing this area. And how are they increasing the area? So these materials which are being used in supercapacitor, they have pores on their surface.
Mhm.
Because of this porous structure, the effective area increases, and as a result of which this capacitance also increases. So then, so it, capacitor can, it has a very high power density, so it can provide quick power for very
But
short duration.
but
Yes,
low energy density.
that is true. So we cannot provide power for a long duration.
Long duration.
So that is why for applications like for coping up with transients or providing primary frequency regulation, we can use capacitor to supercapacitor. So in one of the electric vehicles, they have this one company has manufactured autonomous EV. So they have this supercapacitor plus fuel cell. So there the supercapacitor used for the acceleration, for providing the acceleration, and then for the rest, the fuel cell is used. So high spikes in the power requirement can be met by the supercapacitor.
Handling of supercapacitors will also be a safety issue, no, because of high voltages. That is also an issue.
No, we have capacitor is high. Capacitance is higher. The voltage may not be that high. We are increasing the C value here.
Yeah.
So even for lower voltage, it can work.
Okay.
So let us see. So A is correct option. So now this is the next question. Which of the following is not a benefit of DC over AC? So you were mentioning in the beginning of the lecture. So its control is easy. So what are the other benefits? Can you find out? So we have to see which is not a benefit. Is this is this. Which is not a benefit of DC or AC? Which one is the correct option? DC provides easy control. Control is easier in DC. That is correct. And also in DC we have eddy current, skin effect, and hysteresis loss are not there. They are absent. Then various conversion stages are also available, but we don't have reactive power harmonics and frequency control requirement. There is no harmonics because it is DC. So first option is the correct. This is not a benefit of DC. So why various conversion stages are required? Because we have this solar or fuel cell. So these are DC. So we want to convert them into AC to feed it into the grid. Similarly, for both, this is for both fuel cell and for solar. One conversion stage is DC to AC. But before this DC also we may have one more stage of DC to DC. Because the voltage level of the output of this solar, this V may not be sufficient. So we want to boost the voltage. For that also we need one stage. So here we require two stages. Then again at the load end, because load is DC, we are feeding AC power, we need again AC to DC conversion. We may also need again a DC DC conversion for appropriate voltage levels. So these different conversion stages result in loss of power. So it reduces the efficiency. So if we have only DC microgrid, we can avoid this DC to AC conversion stage. Then again here AC to DC conversion stage. These two stages can be avoided. Let us move to the next one then. Which of the following statement in isolated mode is correct? This is for the microgrid control. And in isolated mode. So in islanded mode, which type of controls are what type of controls are available in islanded mode? So are you there? Okay.
In isolated mode, all will work in PQ mode only.
In isolated or grid connected?
Isolated means islanded, na?
Yes,
Islanded mode, na?
isolated or islanded are same.
Same, no?
So all the converters will work in PQ mode in which mode? In grid connected mode or islanded mode?
No, get connected mode, PQ mode.
Yes, grid connected mode. But here we are talking about islanded mode. So this is true. All DGs operate in PQ mode. This is true for the grid connected mode. Correct.
Hmm.
But islanded, what will happen in islanded mode? Will all the DGs work in VF mode?
No, no. Some will operate in PQ and some in VF.
This is correct.
Yes.
So because in islanded mode we need one
Yes.
reference.
Yes.
Grid connected mode we have the reference. From
Yes.
VCC we take the reference.
Yes.
V and F reference.
Yes.
But in isolated mode or islanded mode, we don't have any reference, so we need one of them to, at least one of them
Yes.
should be able to provide that reference, and
Reference.
others will be able to follow that.
Yes.
So that is true. Some DGs operate in PQ
But
and some
yeah, people some in VF.
yes. So next is this ring DC microgrid is an example of which one? Single bus, reconfigurable, or multi bus?
Multi-bus topology because we are ring, na? Ring
Yes,
is factor.
correct. So here we have this single multi-bus, and then we have reconfigurable. So ring Ring falls in this. No. Ring will come in this reconfigurable. So in single bus, suppose we have this only. This is the single bus, and here we can connect source and load. Here we have different loads, and here we have different sources. Suppose buses are solar, so it will be DC to DC. If we have wind, then it will be AC to DC because AC wind output is AC. If it is fuel cell, then it is also DC to DC. If we have a battery, then also it is DC to DC. So this is a single bus. On single bus, we are connecting all the loads and generating power. But in multi-bus, one load can be fed by more than one bus. So if we have a load here, so here we can have one bus, we can have one source here. So this even we can have one source here. So this is one bus, two buses are feeding this load. So this is a multi-bus. In ring we can have like ring, we can have several buses here. And in between we can have loads and generation at different buses. So if we have a fault here, this can be isolated. Still, the loads can be fed on this generation or from this generation. So when fault is there, it is able to reconfigure itself to provide the to feed the loads by rerouting the flow in the network. Is it okay?
Yes, okay.
Okay, so now this is the next question. Which of the following statement with respect to grid feeding converter is correct? So, grid feeding converter. Which one is correct?
B, they can operate in parallel with other grid feeding converters.
This is not can. This is cannot.
This can.
They can. So this is not the option. This is incorrect. They can operate.
The question is like that.
They can operate independently. They
Yeah.
can. No, they cannot operate independently in islanded mode. Huh? They require grid feeding converter. They require P and Q. No?
Yes.
P and F reference.
Yes, sir.
So they cannot operate independently in islanded mode. The next option is this.
Control.
So they can help in this, no? Because they feed P and Q. So by changing their output P and Q, they can help in maintaining the frequency and voltage.
Yes. Option C is correct.
So option C is correct. So one question is this. I think it will be next question. Yes. So one more another question there. So this is the next question. The converters used for battery, PV, ultracapacitor, and wind system in DC microgrid are respectively bidirectional. So we have to tell which one of them will require a bidirectional and which will require a unidirectional converter. So how do we decide that which one will require bidirectional current or unidirectional?
These are bi-directional, unidirectional, respective to battery, PV, like that. Na? Four.
Yes, yes. So first one is for battery, then PV. So this is for battery, this is for PV, this is for ultracapacitor, and this is for wind. We have to match.
Battery and PV is unidirectional.
Okay.
Is that true? They
So
can,
why do you say PV is unidirectional?
uh, because the current source, na? PV is a current source, and this is just like DC source.
Correct. It is simply a generator. It is not. It never acts as a load.
Yeah,
So it is only giving power. It is not
yeah.
consuming anymore.
The generator the work in one unidirection only. Na?
Yes. So PV is unidirectional.
Battery is unidirectional.
Battery is, why do you say battery is unidirectional?
No, no, clearly charging, discharging.
Yes. So we
Yes,
have both
yeah.
both
Both.
operations,
Yes,
right?
yes, yes, yes.
Charging
Both
is
of it.
there, discharging is there. So in charging it will act as
Yes,
a,
yes.
in charging it will
Charging.
act as a load or generator.
No, as a load, no? As a
Correct.
load.
Yes. And
Charging as a
discharging
load.
it will act as a generator.
Generator.
So we have a bi-directional flow of power.
Bi-directional. Battery will be bi-directional.
So okay, battery is
P-
done. It is bi-directional. PV is unidirectional.
Unidirectional.
Then ultracapacitor.
It discharges in one direction. No, charging, discharging both. Capacitor,
Yes.
charging, discharging both.
So okay, this is
And the
also
bi-direction.
bi-directional.
Yes.
And what about
And
this? Wind.
PMSD wind generator. The synchronous, no?
Yes, this
Permanent
is permanent magnet synchronous generator.
synchronous generator. Can,
So actually, main this bidirectional is based upon the current.
okay.
So there should be bidirectional current flow capability. What is happening even in PV? It
Yes.
can consume some power. It can consume. It does consume reactive power because of these inverters. The inverter they require reactive power. But in that case, although they consume reactive power, but current will always be in the same direction. Current will not reverse.
Yes.
But because of the we change the switching pattern in such a way that it take it can it can take or it can give Q P and Q. So, but current will always remain in the same direction. That is why they are unidirectional. Same is with wind also. Wind will they will also consume reactive power.
Yes.
But here battery and ultracapacitor, the current reverses. That is why this bidirectional is for current. So they have bidirectional current capability requirement is there for them because when they are charging,
Yes.
current is in different direction and discharging the current is in different direction. And also they need to this P and Q they can give inject or even absorb based upon the switching pattern. So, so wind is unidirectional or bidirectional?
I'm having doubt because synchronous machine can act as a generator also, no? Over excited conditions.
In overexcited case, it will provide reactive power.
Yes.
We are using it in generation mode only, not in the motoring mode.
Okay.
If underexcited, it can absorb reactive power. Reactive power absorption or injection is possible even in PV based inverters also. But their current will not reverse.
So only generation will be unidirection only. If we are using in one only generation mode, then unidirectional.
Yes, correct.
Yes.
So which option is correct?
Then option wise will come. First one battery,
Hmm.
bidirectional.
Hmm.
Then PV, unidirectional.
Hmm.
Bidirectional, unidirectional. Then bidirectional, direction. A, first one.
Correct.
First one.
A is correct.
Yes, first one.
Yeah, I was talking about this question. So
Yeah.
grid feeding converters are connected to the grid.
Okay.
How are they connected? So we have to tell whether they are acting
Okay.
as a current source or as a voltage source. So one is grid feeding converter.
Yes, these are high impedance parallel.
High impedance parallel. That means they are acting as voltage source or current source.
No, the parallel, if they are high impedance device and there is a current source.
Correct. So this will
Current.
be current source here.
Yes.
This will be a very high value.
Yes.
This is
Correct.
grid feeding. So here
Yes,
will
sir.
be parallel and high impedance. So if this question was for grid farming, then
Then grid forming,
what should I
grid,
have here?
grid fitting.
So here we are pushing constant P and Q. We are taking reference of voltage and frequency from the PCC, and then we are generating. We are feeding P and Q. In grid farming, we want to maintain a reference voltage and frequency. So, what type of source should this be?
Then will be opposite to that. Na series with high impedance.
Series with no. So, series is correct. So
Yes.
now another thing is whether what this should be
Uh,
voltage or current, or and second question is this R should be low or high. These are the two questions.
no, should be low because it is a series. And
Correct. They,
definitely it should be low.
correct. They should be
Yeah.
low. So this
Yeah.
what about this voltage or current?
Uh, the voltage source now.
Hmm. Correct.
Voltage source.
So this is a voltage in series
Voltage
with
source.
the. So
Low resistance.
this will be the option then.
Yeah.
So voltage in series with the low impedance. So this is correct.
Red reading.
So, do you have any doubt in this week 6 material?
No, no, it was quite good. Quite comprehensive.
No, from lectures, while going through the lectures, did you find anything which you were not able to understand?
Uh, please repeat what you are telling.
I was saying, while going through the lectures, did you find something which you were not able to understand?
This concept, this vector, this superimpose part, that was little bit confusing.
Hmm.
Phasor diagram or what? That was only got clear now today after a lot of discussion.
So, okay.
That was the only uh, little bit difficult you can say to understand. Otherwise,
So, that's now
yeah,
clear, right?
yeah, that is clear.
That is good.
Yeah, that was some difficult to understand how superimposition, how lagging, leading, and that was little bit confusing, but got clear now.
Okay,
Yeah,
that is
yes,
great.
this introduction was very helpful for that.
So what about others? Others, do you have any doubt in this week 6 material? If no, then yes. Are you saying something? shall we move ahead then? Okay, then if no doubts, then let us see the next question. So this is the
Yes,
next
sir.
question. Which of these is not microgrid ancillary services during grid connected mode?
Should we black start
So
in
we
grid
need,
connected mode, no?
yes. So when do we need this?
Uh, Not microgrid ancillary services in grid connected mode.
So when do we need this flag start services?
In island mode only, no?
Yes, but why do we need this flag start?
When complete power failure occurs, then system has to be black started. Auxiliary services power requirement is there.
Correct.
Yeah.
That's true.
Yeah.
Correct. Oh, yes, questions are over for this week. If you have any doubt, you want me to go through some topic again, you can tell. I can explain them again. We have 15 minutes left. Anything that you want to discuss? One thing we can do is, suppose here, Jay, can you answer this question? So,
Which one?
suppose if this current is 100 ampere
Yeah.
and this is 1400,
Just 1400 minus 100
yes,
is like that
this
simple mathematics now.
so this is correct for
Yeah.
when, because
Yeah.
we are only talking about the absolute sense.
Yes.
Suppose I say that the current
Yeah.
drawn by the load is 100 angle
Yeah.
minus, it will not be that much, minus 15 degrees. And the fault current is 1400 angle minus 30. Now you
Mhm.
have to tell about the direction of fault current. Will it be in front of relay or behind the relay? Can you do that?
100 minus 15. Please repeat question once again. Uh,
So same question is there, but I have replaced this current by this. Now this current I have given in phasor form. Now
okay.
this is 10 angle minus 15,
Mhm.
and this is 1400 angle minus 30.
Yes.
So now we have to find out whether the fault is behind the relay or in front of the relay. So it is like this. So we have a relay here, and this is the fault current. This is 100 angle minus 15, and this is this current we are measuring here. This is 1400 minus 30. We have fault. Now we have to check whether fault is here or here. That we want to know. This is the question. Now, can we do it? If yes, then how should we proceed?
That should be in same quadrant, no? Because angle difference is only 25 degree. 25 no, means 15 degree only.
So it will depend. It will it will depend upon. So we are saying. Uh, This is the pre-fault current,
Yes.
right? And this is this is the fault current. This is small and this is large. This is somewhere, let's say 0 degree. This is the fault current. Fault. So now we have to take reference of I fault minus A1 free. So it will be this, right? Correct? Right? Is it correct?
Uh,
And what is the angle of this? It is phasor like this, something like this. And we want to find angle between this I. This is delta IF. We want to find this angle.
mhm. Minus. We'll add, no? Both. We'll add.
No, we want to subtract the pre-fault current from this fault current. Then we will get this IF. But what we are doing here is we are doing IF plus. So IF plus superimposed component will be equals to I pre. No?
Yes.
We are doing this. We are doing same thing here. So let me make it again. Let me try it again. So this is our 0. So this is IF, I pre,
Okay.
and this is our fault current, IF. Now I want to subtract IF minus I pre. So if you do that parallelogram law, then you have to take negative of this I pre, right? Minus I pre, and then you will add these two.
Okay.
You will do like this. You add it like this. So it will be like this. Then you take the resultant. So it will be like this. Or what you can do, you add here. It is same. No? You add it here. So if you add IF and the superimposed component, you will get the pre-fault current. Is it okay or shall I?
No, no, it's okay.
Hmm. So we are talking about this current, this phasor, and we want angle between this. So we want this delta phi is angle between this superimposed current and pre-fault current. This is the phi.
Yeah. Mm.
So now this angle is positive, right?
Yes.
Because this IF is here, delta IF is here, I3 is here, so this angle is positive. So we have a fault in F. We have a fault here. Is it okay?
It's okay. Okay.
So if fault F2 is there, so I pre will remain same.
Yeah.
IF will change.
IF will change definitely.
Yes, IF will change. IF will become like this, something like this. IF is here.
like this.
So
Yes.
now we want I3 is, this will become the superimposed current. Now I3 is leading. So current, the angle will become negative. Correct?
Mhm. Yes. 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 Correct.
So this is the main thing. This is the superimposed entire this technique is based upon this concept. This directional relay, how it works, what current are we taking, which are the angles, what the angle is between which two quantities. So in directional conventional direction relay, this voltage is the polarizing quantity and current is the operating quantity, right?
Yeah.
So what is the polarizing quantity here in superimposed current based direction relay?
Will be
It will be
for these two new figures, na?
no, in general, this is general question
Yeah.
that for a superimposed current based relay,
Yeah.
which one will be the polarizing quantity and which one will be the operating quantity. So what in conventional relay, what are we doing? We taking voltage as a reference and we measure the
Reference current. Yeah.
current angle of current with respect to voltage.
Yes.
So what are these two quantities in case of superimposed? What is here? What is here? Which one is the reference? That can you relate? So if you recall this formula of angle, from there you can tell what is the formula for this. How do we calculate this angle? Can you tell?
I have to recall.
No, we discussed just now. I wrote the formula, right? You can see here. See this. See this formula. This is the formula. So we are taking difference between which two angles, which two current, which two quantities, angle of
Yes.
which two.
Superimpose minus pre.
Yes. So in
Yeah.
conventional, we are doing this
Yeah.
angle of voltage minus current.
Yeah. In this case, superimpose minus pre.
So which one is the polarizing quantity here?
Superimpose
Hmm.
what? Yeah. Superimpose.
Yes. So this is polarizing and operating is this
Yeah. Operating is
current.
pre.
This positive sequence current.
Yes.
So
Positive.
polarizing quantity is superimposed current and this is
Uh,
positive current,
positive.
positive sequence current.
Positive sequence. Yes. 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 Now clear.
Yes.
Now I'll read once again lecture. Then 100% everything will get clear.
Okay. Yes, you can
Lot of clarity has. Lot of clarity has come.
it's good that these sessions are helping you.
Yes. Yes. Definitely.
So 3 minutes are left. You want to ask something?
No. No. It's okay. Taken a lot of pain. It's okay. Now some. We should also do something. Yes.
So did you
Yeah.
did you do the assignment?
Yeah. Yeah.
So was it? Did you find anything difficult?
No assignment. Some mistake I have made in last assignment, but now I understand what were the basic concept where I was not through. So, so
Okay.
actually I have to read some
Yes.
reference also. That's a very useful session. Yeah, yeah. Very, very useful.
Thank you.
Yeah. Well, I think time is over. You can ask other person also if they are. Then we'll wind up. Yeah.
Yeah, sure. So Sindhu, I think. Sindhu, are you there? Do you have any doubt?
No, sir.
So are this session helpful?
Yes, sir. Very much helpful, sir.
Okay, so
Thank you so much, sir.
thank you. If you have any doubt, you can ask even in next session. We'll be having the next session same time next week. So if
Okay,
you have
sir.
any doubt in up to what has been covered till now, so you can ask in assignment
Okay,
or
sir.
anything. Next week we'll discussing the week 7 material. So if no doubts, then I think we can wind up.
Yes, yes, we can.
Okay then, let us meet next week same time. Thank you for
Yeah, thank
joining and actively participating.
yeah, yeah. Very useful session. Thank you. Thank
Thank
you.
you.